Welcome everyone again to Zahid's data mining channel. My name is Zahid Islam. I'm an associate professor in the School of Computing and Mathematics at Charles University. So today we are going to talk about decision trees and decision forests and how we build them, etc. So we'll do that by introducing a paper that we recently published in a top quality journal called Expert Systems in Applications, and the name of the paper is Forest PA: Constructing a Decision Forest by Penalizing Attributes Used in Previous Trees. A decision tree is like a tree structure. It's a tree-like structure, as you can see on this figure here, and a decision tree can be built automatically from a dataset by using various existing tree building algorithms. So what is a dataset? A dataset is, by dataset we mean something like this, a two-dimensional table where rows are records and columns are attributes of the dataset. This is an example of a sporting club dataset where we can consider that each row is representing a soccer match of that soccer club. Whenever they played a match, they recorded the information belonging to that match. And thereby they gradually build a data set like this. Here the first attribute is venue, if they played at the home ground or away, and who was the goalkeeper, and there can be many other information. This is just an example of a data set. And finally, in a data set you can have a label or target attribute like result, whether they won the match or they lost the match, that sort of information. Now when you have a big data set like this, then it's very difficult to understand the pattern or knowledge from the data set. Then you may actually want to build a decision tree like this that will tell you, okay, if the venue is home and goalkeeper is Matt, then they lost the match. They played 2 times under this situation and they lost both times. So it can give them some idea why they are winning and why they are losing. Now this is just a toy example, but when you have a very big data set, this can be very meaningful. Now what is a decision forest? A decision forest is, instead of just building one decision tree, if you build a number of decision trees from the same dataset. So if you build a series of decision trees, an ensemble of decision trees, then together that is known as a forest. And the advantage of a forest is, like, it can actually, if you build your forest carefully, it can actually discover or extract more knowledge than just a single tree. It can give you a 360-degree view, almost like a 360-degree view of your dataset. More patterns can be revealed. That's advantage number 1. Advantage number 2 is generally when you build a careful or a sophisticated decision forest, then generally it also gets higher prediction accuracy than a single tree. Together, a forest can make better prediction. How do you build a forest? I will quickly introduce an existing approach called bagging. And say, for example, this is your dataset, and when you want to build multiple trees from this dataset, one simple and straightforward approach can be, you can have multiple bootstrap sample of the dataset. How do you have a bootstrap sample? How do you prepare a bootstrap sample of the dataset? You can actually make a dataset from the original dataset by randomly picking records in that dataset. By randomly picking records in that dataset, meaning if you randomly pick records with replacement from the original dataset, then the chance will be high that you will get around 66% records from the original dataset in your bootstrap sample. And then you can build a tree from that bootstrap sample. Similarly, then you can again do the same thing. You can randomly pick some records with replacement and you will have a different bootstrap sample, and then you can actually build another decision tree from the second bootstrap sample, and you can keep doing it as many times as you want, so you can have as many trees as you like. Now I will quickly introduce our recent decision forest algorithm called Forest PA, and that has been published in Expert Systems with Applications. It's a very good journal, so feel free to go and read that paper. If you go to my webpage, you can find me out by Google searching me by typing my name Zahid Islam, and you can see my webpage, and then there is a publication link. If you go to my publication link, you can see the papers in that web page, in that link. And for all of these papers, most of the papers, maybe with some exception, rare exception, I have a link for the preprint version of the paper in ResearchGate, so you can actually download the paper from my ResearchGate. That will be the preprint version, but you can go online and find the paper from Expert System as well. Now, what we do in that paper, we said, okay, so we will again build multiple trees, but look, in a forest, generally the accuracy of a forest will be higher if you can actually find or build trees in the forest that are individually very accurate, right? Each of the trees are very accurate. Then generally the forest accuracy increases. That's condition number one. Generally, condition number two is if the trees are diverse. So if you have the trees that are different from each other, that are diverse from each other, then they contribute better. So with these two goals, we said, okay, in Forest PA, this is how we will build a forest. First, we will have bootstrap samples, as I showed you before. From the original dataset, you get your first bootstrap sample, and from that, as I showed you before, build your first tree. So once you have the first tree, then before you build your second tree, you need to assign weight to the attributes that have been tested in the first tree, so that the chance of the same attributes being chosen again in the second tree will go down, right? And that way we are kind of encouraging diversity. So we are assigning weight. Originally, the weights before you build the first tree, we assign the weight 1. 1 is the maximum weight and 0 is the minimum weight, right? So we assign weight 1 to all attributes, all columns of the dataset, and that thereby we build the first tree. So it is fair game for all attributes. Once these attributes AI, AJ and AP are chosen in the first tree, then we assign some unfavorable weight to these attributes. That's the basic concept. So the chance, so unfavorable weight means less than 1. Okay, so the chance of these attributes being chosen again in the second tree will be less, and therefore we are encouraging other attributes to come up and be chosen. So how do we do this? First we build the first bootstrap sample, build a decision tree, and then if the attribute is chosen at the root node, then we assign a weight which varies within the range of 0 and e to the power minus 1 over lambda. Lambda is the level. So if it is the root node, then lambda is 1. So that means the lower range of the weight assigned to the root node will be between 0 and 0.3679. So it can be either 0.3679, it can be, so randomly, we pick randomly within this range. So the weight is very low. You can see the maximum possible weight for the root node will be 0.36. So instead of 1, it becomes 0.3. So that means, well, it's heavily punished, and the chance of this attribute chosen in the second tree will be very low. That's the idea. And for other attributes chosen in the second level, third level, fourth level, etc. of the tree will be according to this formula. So we will again assign weight, and you can see for a second level attribute, the weight will vary between 0.368 and 0.605. So the lower the level, the chance of higher weight is high. So you will have higher weight. So we don't punish them much. You are tested at a very lower level, you are okay. You can come back. But if you are tested at the root level, okay, we want you heavily not to come back again. Something like that. That's one step. And the second step is we have a weight release approach as well. Weight release is sigma I, and this is 1 minus omega I, when omega is the current weight, and neta plus 1 minus lambda. Neta is the total depth of the tree. So what is weight release? Say for example, AI, AJ, and AP are tested in the first attribute, AI, AJ, and AP, and then say when we build the second tree, we have a second bootstrap sample, we have a different weight distribution based on AI, AJ, and AP has got some weight, and other attributes like AK, AL, etc. Those guys don't have any weight, so still, I mean, no punishment, so still one full weight, one. So we get a different tree now here. Say for example, AP is not tested in the different tree, in the second tree. So when AP has not been tested in the second tree, for building the third tree, AP's original weight will increase a little bit. That's a weight revival process. Otherwise, we'll run out of good attributes. If we just keep on assigning weights and don't let them revive, then at some stage, all good attributes will have so heavy punishment, so low weight. So for building next tree will not have many good attributes, so individual tree quality will suffer. That's why we have a weight revival process as well. And that process involves a few issues like how much weight you was assigned on that attribute. The lower the weight assignment, the higher the chance of weight increase. If the weight assignment was very low, then we will let it increase a little bit. That's one thing. And also where the tree attribute was tested. If the attribute was tested at the root node, then we will let it grow slower. And if it is tested at a very bottom level, we'll let it grow faster. That sort of approach. So the bottom line of this, if you read the paper, you will understand it better. But bottom line of the paper and the approach is that we want to make all the weight distributions for each and every tree different from others. So weight distribution of the attributes need to be or aimed to be different from the trees, from the other trees. That way, we kind of wanted to encourage to have different sort of trees. And actually we do that. For example, here, if we see an example of first 3 trees built from a data set called class identification, we can see that the trees are very different from each other. And we have also made extensive experimentation on that based on 20 data sets, and we wanted to see 3 things: in ensemble accuracy, the accuracy of the whole forest; individual tree accuracy, how individually each tree is accurate, how accurate they are; and individual tree diversity in the forest, so how diverse they are. So diversity is in this one measured by kappa, AIK, individual average individual kappa, average individual accuracy, and ensemble accuracy. So you can see from this diagram that Forest PA's average ensemble accuracy is 82.5, which is highest among all of these, bagging, random subspace, based on these 20 data sets only. And its individual accuracy, if we look at the individual average individual accuracy, you can see it's much higher than random forest. So random forest is somewhere there, and so Forest PA is average individual accuracy is higher. So random forest trees accuracy is not as good as this one, but random forest is more diverse. As we can see, kappa, lower kappa means more diverse. So you can see this is random forest diversity. If you go there for Forest PA, you can see Forest PA is not as diverse. So Forest PA loses a little bit of diversity, but it achieves a little bit more individual accuracy, as a result of which it achieves higher ensemble accuracy. We divided the data set into few categories: low dimensional, high dimensional, low size, high size data set, and then we checked Forest PA's accuracy compared with other existing techniques accuracy, and we find Forest PA is better than others. And this is the paper. We have few other papers on the similar direction. Feel free to read them, and thank you very much for watching.